So therefore that is Cn. And the question is that, is there a closed formula for this, right? So this is something we can see. Now, can we find a closed formula? So for each k, there are k ways to plan the right. So as we mentioned, right, k ways to plan the combinatoric spots with one holiday, and therefore the generative function, right, we can find separately is for this. Right, the counting sequence is summation k greater than equal to 1, k into x raised to k, right, which is the generative function. And then similarly, generative function for the L choose 2 is to plan 2 labs in L days, right? L is equal to n minus k. And that is b of x, which is summation L greater than equal to L choose 2 into x ratio, because we need at least 2 days to choose from the for the labs. So therefore, we have these two generative functions, and we know the product of the generative functions will give us the so if you can solve independently for this, we can use that to get a closed formula for C of x. So that is the idea. So what is A of x? A of x is x into summation k greater than or equal to 0, k plus 1 x raised to x, right? Because I take 1 x outside. And this we already know, right? Which is x by which is 1 by 1 minus x whole square, right? So summation k plus 1 x raised to k is 1 by 1 minus x whole square. And then with the x outside, I get x by 1 minus x whole square. Similarly, b of x is summation L greater than or equal to L choose 2 into x raised to L, which if you remember, if you take the derivative once, right, you will get n plus 1 into x raised to n minus 1. Now, if you take the derivative twice, you will get n into n, n into, not n plus 1, n into x raised to n minus 1. So, I will get n into n minus 1 into x raised to n minus 2. Right? So, therefore, I will get L into L minus 1 into x raised to L minus 2 into x raised to L minus 2. And now, I can take the, L into L minus 1 by 2, I can take the 2 outside, right? So, I will get x square by 2. So, I can write this L choose 2 as, summation, and taking x square outside, I will get x square by 2 into summation L greater than equal to L into L minus 1 into x raised to L minus 2. But this, the second part, right, which is the part inside the summation, is precisely x by 1 minus x whole cube, right? So because the derivation, derivative of the derivative of derivative of 1 by 1 minus x 3 times, right? So no, 1 by 1 minus x whole cube, which is the derivative of 1 by 1 minus x, the second derivative, the third derivative, right? No, second derivative. So therefore, I will get x square by 1 minus x whole cube as b of x. So therefore, so what do I have? I have summation L greater than equal to L choose 2 into x raised to L, which I wrote as summation L greater than equal to L into L minus 1 into x raised to L minus 2 with x square by 2 outside. And this is the second derivative of the series summation x raised to N, right? And therefore, right, this is the second derivative of summation x raised to N, which is by the generative function of this, the way to represent this is 1 by 1 minus x. So its second derivative is 1 by 1 minus x whole cube, and therefore I get this as 2 by 1 minus x whole cube, right? Yeah, so 1 by 1 minus x, the derivative is 1 by 1 minus x whole square, but then its derivative is 2 by 1 minus x whole cube. And therefore I will have x square by 2 into this will be x square by 1 minus x whole. So that's how I got, right? Okay. So then the C of x by the product rule, right now is that A of x into B of x, which is x cube by 1 minus x whole raised to 5. But now 1 minus x whole raised to 5, right? We can find out by Taylor series expansion, and then we need to shift the degree by 3, by because there is an x cube. So which is, I can write as x cube into summation n greater than 0, n plus 4 choose 4 into x raised to n. Okay, this is again by taking derivative 5 times we can show that this is precisely the case. And therefore I take the x cube inside this. I can write as summation n greater than 3, right? Because from 0 I shift by 3, and therefore n plus 4 becomes n plus 1, right? So n becomes n plus 3, right? So therefore n plus 1 choose 4 into x ratio. So therefore the coefficient of x ratio n is n plus 1 choose 4, and therefore I have a formula for Cn, right, which is n plus 1 choose 4. So summation k equal to 1 to n minus 2, k into n minus k choose 2 is equal to n plus 1 choose 4. So I can solve now this summation also, right? So I get I get a closed formula for the summation, which otherwise would be much more difficult to come up with. Okay, so you can try this without using generative function if you want to do this. And similarly, the product actually helps to compute these things easier. That if you had the this summation, then you use the generative function method, it will be slightly more difficult. Now, if you remember your partitions, right? So let us define the number of partitions, right, of the integer n into parts of size at most k. Okay, so and denoted by p dash of nk as the number of such partitions. Okay, so we want to partition, but then each part has size at most k. Now we want to show that the generative function for this sequence p dash of nk is product I equal to 1 to k 1 by 1 minus x raised to y. Okay, summation n greater than 0 p dash of nk x raised to n is product I equal to 1 to k 1 by 1 minus x raised to y. So this is the generative function for the partitions of n into parts of size at most k. So let us try to do this. So what is given to us is product I equal to 1 to k 1 by 1 minus x raised to y. So let us write it as product of series, right? So I have 1 by 1 minus x raised to y for I equal to 1 to k. Each one gives a separate series. So therefore I get first one is when I equal to 1, 1 plus x square plus etc. Then when I is equal to 2, I will get 1 plus x square plus x raised to 4 plus etc. And similarly, when I is equal to k, I get 1 plus x raised to k plus x raised to 2k plus etc. Right? Now, what is the coefficient of x raised to n? Right? From here, right? Coefficient of x raised to n is of the form, right? If you look at this product, coefficient of x raised to n is of the form. From the first, you will get, let's say, some t1, right? Because the coefficient of right x raised to n, I can say that it from the first time it comes as like t1 times 1. The second time it comes as, because it's a multiple of 2, it's t2 times 2, right? 2 times t2. Then from the third one it is 3 t3 etc. From the kth one it is k tk, right? But now this whole sum should be equal to n, right? So from the first you will get, let us say, if you are taking the the T1th power, right? So it is basically x raised to T1, right? So T1 plus second one, if I take the T2th term, then I will get 2 times T2, right? In the coefficient, right? 2T2. Similarly, Tk term, if I take from the last one, then I will get k times Tk as the exponent. So, and sum of these exponents must be equal to n because we are looking at the coefficient of x raised to n. Now, this is how I get the coefficient of x raised to n in this product, right? From anywhere, if I get x raised to n, this is how it is going to come. Now, I want to see this in a different way, okay? So, the first one is basically 1 plus 1 plus 1, etc. T1 times, right? Which is 1 times T1, right? And 2 times T2 is 2 plus 2 plus 2, etc. T2 times. And the k times Tk is k plus etc. Tk times. So this choice I can see as choosing, right, T1 copies of 1, T2 copies of 2, and Tk copies of k. And all of them sum to n, and the maximum value is k. So therefore, this generative function actually represents the partition of n, where each part is at most k. On the other hand, we can also see something else, right? So each partition, right, you can see that clearly correspond to a product, right? Because given a partition, we can basically say that, like take the number of times I appears, and this is a choice of x raised to I times that number, right? And therefore I get a one-to-one correspondence in between these two. So I get this. Now I can also look at, so this is a more interesting part of looking at the generative function. This we observed earlier, but let us put it again. So if you want to look at 1 times T1, 2 times T2, k times Tk as parts. So each of these I can see as, instead of looking at this one as the parts, right? 1, 1, 1, 2, 2, 2, etc. as parts, and at most k, right? Value at most k. I can also see the same summation as, right? 1 times T1 is a part, right? So it comes, and 2 times T2 is a part, 3 times T3 is a part, etc. K times Tk is a part. So I can also see this as the number of ways of decomposing n into parts, at most k parts, right? Because there cannot be more than k times here. So therefore, we get a partition of n into at most k parts, and this agrees with our, as I mentioned, our earlier observation that, the number of ways of partitioning n into, right, partitioning the integer n into at most k parts is precisely the number of ways of partitioning where each size is at most k. So as a corollary, we can also get the generative function for P of n, which is the partition of n, right? Summation n greater than 0, Pn of x raised to n is product I equal to, or k equal to 1 to infinity, 1 by 1 minus x raised to k. Because here we are not putting any restrictions on the number of parts, right? So k can vary from 1 to infinity. It can be anything. But of course, once the k exceeds n, you will see that, this will not give you any coefficient of x raised to n, therefore we don't have to worry about that. But for every n, we have this, so therefore I can define the summation overall in 0, Pn of x raised to n as product k equal to 1 to infinity, 1 by 1 minus x raised to k. So this is a nice way to come up with the generative function for related things. Now a homework question, okay. So show that the generating function for partition of n into distinct parts, p n comma dist, right, is equal to the number of ways of partitioning n into odd parts. Okay, so p n odd is denoting, p n odd is denoting the number of ways of partitioning n into odd parts. So each part is odd, and uh, and And Pn distinct is the number of ways of partitioning n into distinct parts. So each part is distinct. And these two are identical. So this is what you want to show. The generator functions are the same. So, and using this, show that there is a bijection between the corresponding sets. Of course, that comes immediately. So we need to show that the generative functions for these two are the same. Second question asks you to solve the recurrence relation Cn is equal to summation I equal to 0 to n minus 1, Ci into Cn minus 1 minus I, where n is at least 1, with C0 is equal to 1 as the initial condition. So find C of x and then deduce the formula for Cn as the coefficient of x raised to n in C of x, right? So this is what you should do. Okay. Now we are going to look at the composition of generative functions. Okay. So what I mean by composition is that I can substitute one function instead of the variable of the other function. So if I have, like, for example, a of x and b of x, then I can talk about a of b of x, right? So x becomes b of is replaced by b of x. So wherever x appears in a, I replace it with the b of x. So then what happens according to the combinatorics, and that is the question that we want to look at. So let an be the number of ways to build, let us say, a type A structure on an n element set. Okay, so we have an n element set. Then I want to look at the number of ways to build a type A structure on this. Then on the empty set, we assume that there is no type A structures that you can build. Okay, because this is a necessary assumption, because as you will see when we are going to substitute this inside, you will see that if you can make empty structures out of a set, then you have way too many objects that you can make out of, and then it will not become a converging sequence. So what we will do is that we will assume that a0 is 0, right? So on empty set you cannot make any structure of type B. Then Bn, let's say, denote the number of ways to build type B structure on an element set, and B0 is 1. Okay, so this assumption is not strictly necessary, but it will be good for us in this type. Okay, so the B0 equal to 1 is not really necessary, but A0 equal to 0 is strictly needed. Now let Cn be the number of ways to split the set 1 to n into non-empty intervals. Okay, and then build, let's say, A type structures on each interval, and build B structures on the set of intervals if and if a, b, c represent the generative functions for a n, b, n, and cn, then we have c of x is equal to b of a of x. Okay, so let us look at it again. So what we are going to do is that, given an element set, I partition into non-empty intervals. Okay, so so the set is 1 to n, right? Set 1 to n, partition into non-empty intervals. So let's say 1 to let's say something 1 to 5, right? And then 5 plus 6 to, let's say, 9, right? And then 10 to 21, etc. Right? So we put it into non-empty intervals. Then for each part, right, 1 to 5, I'll put an A structure on this set. Then I put another A structure on 6 to 10, and similarly I put A structure on the remaining part. Now then on the set of intervals, right, I put a B structure. Okay, so there is how many ways I have partitioned. that many elements will be there. So each interval becomes an element of the set. And then on these intervals, I put a base structure. So this, if I am doing, then the generative function for the number of ways, to build this structure, which is Cn, is let's say C of x is the product is the composition of B of A of x. That is, you substitute for x in B of x with A of x. So there is a bracket missing, I think. B of A of x. Now I will give you a sketch of the proof. So let us see why this must be the case, right? So the number of ways to build type A structure, right, on let's say k disjoint intervals is A, right, A of x whole dash k, right? I mean type, I should say type B structure, right? No, type A structure on yeah. So the number of ways to build type A structure on k disjoint intervals, right, is the product of for each interval we want to take the product. But then since we have exactly k intervals, if you assume k to be fixed, then it is basically the coefficient of ax whole raised to k, because a of x we are doing for each of the k intervals I'm building a structure. So whatever is the number in that interval, I have the generative function will be a of x, right? So a of x is the generative function for building type structure array for any thing, right? Then if you have I elements in that particular interval, it happens to be I elements, then the coefficient of x raised to I will give you the number of ways to build, right? So now if I take so this is the nice thing about the generative function, right? So now since I have a of x, I build on the first one, then the second one I am building another again a of x, third one I am building again a of x, etc. Right? I mean type A structures. So let us the number of ways to build the type A structure on the k disjoint interval is the product of the generative functions, each of them, right? So f x into f x into etc. k times. But then if I start with an n element set, right? If I start with an n element set, then the number of ways of doing this is the coefficient of x raised to n in a of x whole raised to k. And why is this? Because if I look at the coefficient of x raised to n, how the n came about, right? So if n has come out from this product of k times, it must have chosen some values like n1, n2, etc. from each of the k times, right? So that is how I get coefficient. The summation of n1 plus n2 plus etc. is equal to n. The coefficient of x raised to n comes in that way. So therefore, if I have taken from the first part, right, and the second part, and then the third part, etc. up to kth part, then coefficient of x raised to n precisely says that number of ways of doing that when I have exactly let's say 2 elements here, 5 elements here, 7 elements here, etc. Right, for a particular choice and for all possible such choices, right? So because we are looking at all possible ways to partition and then do this, a of x whole raised to k, coefficient of x raised to n a of x whole raised to k precisely gives the number of ways of doing this. But then we are going to build B structure on the k set, right? Now how many ways we can do that? That is precisely bk ways, right, on a k element set, right? So because we are partitioning into exactly k intervals, and each interval I am considering as an element, and then I am going to put a B structure on this interval. So therefore, there is precisely bk ways to do that. So for any fixed k, right, I have exactly bk ways to build a structure once I get the k objects of the type A from this. So there is precisely bk ways to do that. But for for all possible choices for the the splitting of a into this, we get we get it from a of x whole raised to k, right? To divide into exactly k parts and doing this, and therefore it is basically summation, right? K greater than 0, bk into a of x whole raised to k. Of course, we are looking at the coefficient of whatever in the appropriate value. But now, which is the definition of b of a of x, right? So therefore, this is a more, this is just a sketch of the proof. We can formally prove this, but I don't want to go into the details of this. But this I should tell you enough to understand why this. I mean, now, of course, you have to think about this a little bit to see how the generative function plays, because without much experience, how a of x whole raised k, I can use it as a substitute for a number, right? That will not be immediately clear, but think about it and then get back to me. Now, an example, right? So we have n persons standing in a queue to buy, let's say, some books, Harry Potter books or something. Right? People stand in queue to buy this. Now, they were split at several places to non-empty queues. Okay, so some person comes, like some clerk or somebody who comes and then says that, okay, you are standing in queue. Let us split you into several parts by putting some barricades or something in between. Then another guard comes and then says that, okay, they call some subset of this blocks of people, right? So they have several blocks of people, right? The queue is partitioned, right, into several blocks, and then some another guard comes and then say that, okay, some subset of these guys and say that, okay, let us all go to my shop. I will give you faster access to the book. Here you are waiting in the queue, so let me take some of you guys from here and here. Then I will take you to my shop. I will give you a better deal there, right? Now, how many ways this can be done? Okay, so let us solve this. So how do you solve this? So we know that for the number of ways of let's say choosing so number of ways of choosing number of ways of choosing this first type of things, like that is basically split into several places. And what does that guard do? That guard does nothing, right? So what the first guard does is to basically just split the queue into several parts, but he does nothing else, right? So he doesn't modify it anyway, and he don't put any structures. The queues are standing as it is. So therefore, there is exactly one way to do nothing, right? Once you split at several places, you have the queues, and we do nothing, right? So when we were defining this, what we said is that, right, A and B the number of ways to build type A structures on an element set, and the and then Cn, right, was the number of ways to split n into let's say non-empty intervals, and then build A structures on each of the interval, right? But here, what is the A structure? There is nothing, right? Because we are just splitting the interval and doing nothing, which is basically the coefficient is 1. There is precisely one way to do nothing with it. So therefore, I can say that AK is 1 for every K, because after splitting, I don't do anything. For whatever K, I get K intervals, and that's it. So the generative function for A of x is x by 1 minus x, because we have K greater than or equal to 1. And A0 is 0, right? Because if there is 0, guys, there is no way to split. We don't allow non-empty right, structures. So therefore I0 is 0. So therefore I have x by 1 minus x, which is a of x. Now bk is 2 raised to k, because why is that? Like we have to choose some subset of the k blocks, right? There is k blocks, and I want to choose some subset. There is even the subset can be empty. He may not be able to call anybody, right? Because maybe the other guard will come and say that, okay, you cannot steal our customers, right? So anyway, so there is precisely 2 raised to k subsets possible, right? So of the k blocks. So bk is 2 raised to k, right? We are just choosing the subsets and then taking it to its place. So therefore b of x is 1 by 1 minus 2x, right? We saw this before, right? 2 raised to k is the sequence, then we have b of x is 1 by 1 minus 2x. And now we apply the composition rule, right? So b of a of x is 1 by, now a of x is by x by 1 minus x. B of x is 1 by 1 minus 2x. So substitute for x with x by 1 minus 2x, right? A of x, which is 1 by 1 minus 2x by 1 minus x, which is 1 minus x by 1 minus 3x. So therefore, from this, I can get 1 minus 3x will give 3 raised to n x raised to n, and then you multiply with 1 minus x and look at the coefficient of x raised to n, that is 2 into 3 raised to n minus 1. This is something you can verify. For n greater than equal to 1, I have this. So we can verify that there is precisely 2 into 3 raised to n minus 1 ways to do this. So here is a homework question. We have n children who is standing in a line, and the line was split at several places, and one from each section, right? Let's say non-empty sections are non-empty, was made the leader of his team, right? Because each section is non-empty. I can choose one person and then make him the leader of his team. Then show that let's say ln is equal to 1 by root 5 into 3 plus root 5 by 2 whole raised to n minus 3 minus root 5 by 2 whole raised to n. Count the number of possible ways of doing this. Okay. So n children stand in a queue. Line was split at several places. One from each section was made the leader of his team, and the number of ways of doing this is counted by this formula. And then once you find this formula, use it to find L2, L3, L4, and L5. Okay, let us look at a couple of more applications, more from the real world type questions. So let us say that we have we have 3 types of objects are given, right? Let's say A, B, and C. Now, given these 3 types of objects, we are told to pick, let's say, either 0 or 1 or 2 A's, then 0 or 1 copies of B's, and 0 or 1 copies of C. Okay? Then you can ask how many ways to pick K objects from here. Okay? So whatever could be the objects. So 3 types of objects are there: type A objects, type B objects, and type C objects. And you are given, you can pick either 0 or 1 or 2A, 0 or 1B, and 0 or 1C. So how many ways one can do this for to picking K objects? So let us denote by Bk the number of ways of doing this. So the generative function for this sequence Bk is B of x summation Bk into x raised to k. Now, what is precisely B of x? So let us look at, so to count B of x, I am going to use a slightly different method. Okay. So if you look at the following, right? So I want to choose A. Okay. So I'm going to look at the function ax whole raised to 0 plus ax whole raised to 1 plus ax whole square. Then I take the product with bx whole raised to 0 plus bx whole raised to 1, and then take product with cx whole raised to 0 plus cx whole raised to 1. Now, when I take the product of this, right, and look at the coefficient of x raised to, let's say, k for some number. So what is x raised to k coefficient coming from? So if I choose x raised to k as, let's say, ax whole raised to 1, right? Then bx whole raised to 0, right? And then cx whole raised to 1, right? Then the n will be 2, right? And then what does this choice represent? This choice represents that I have taken 1a, right? Because ax whole raised to 1. Then I have taken 0 b's, b because bx whole raised to 0. Then I have taken exactly one type C object, which is Cx whole raised to 1, right? I could get to in another way maybe, right? I can choose Ax raised to 2, Bx raised to 0, and Cx raised to 0. So this way I can get to, right? Similarly, I can just take two A type objects. Similarly, I can pick one B type object and one C type object and choose nothing from the first part, Ax raised to 0. So this tells you the choices of A are either 0, 1 or 2, right? Because Ax power 0, X power 1, X power 2. Similarly, Bx power 0, Bx power 1 and Bx power 2, right? So this will tell you how many A's are chosen, how many B's are chosen, how many C's are chosen, right? So you will get A square, right? X square, right? And and B, let's say B square or bx, a square x square bx and cx. Right? So I will get x raised to 4 with a square bc, right? So I have to choose two a's, one b and one c. Now this is one possibility. So I have several such possibilities. But now how do you put them together to find b of x, right? So observe that, like ax whole square says that the choice is of a, and then I am taking two of them, right? X square tells it is 2, and then a says that it is choosing a. But now it doesn't matter, right? We want to find how many total ways to do this. So it doesn't matter, maybe I have taken 2, but I just need to make sure that I get k only, right? So it doesn't matter whether I take two a's, one b and one c, or like one a, two b, and like in this case there is no two b, but or one c. But as far as the total is k, I am fine. So therefore, I can substitute for a to be 1, right? I take the product 1 plus ax plus s square x square, 1 plus bx plus 1 into 1 plus cx. And in this product, let me put a equal to 1, b equal to 1, and c equal to 1. So that says that, okay, I'm choosing 2 from the first part, 1 from the second part, 1 from the third part, or 2 from the first part, 0 from the second part, and 0 from the, 0 copies of b from the third part, etc., right? Which is choosing 1. This will tell you the number of choices. So the generative function now I can get by substituting for a, b, c equal to 1 in this, and then I will get it is 1 plus 3x plus 4x square plus 3x cube plus x raised to 4. And what is this generative function tells us? It says that I have the choice of objects at most 4 of them, right? I mean, k cannot be more than 4, and if k is equal to 4, there is only one way to do that, right? And if k is equal to 3, there are 3 ways to do it. If k is equal to 2, there are 4 ways to do it. And if k is equal to 1, there is 3 ways to do it. And if k is equal to 0, right, there is only one way to do it. I choose nothing, right? So this tells us the solution for this. So let us verify that, right? One can verify that also for such an equation. So how many ways to choose? There are 4 different ways to choose 2 objects, right? So let us see how this can be. I can choose 2 type A objects and nothing from B or C. That is one way. Then I can choose one type A object and one type B object. That is the second way. Then I can choose one type A and one type C object, which is the third way. Then I can choose nothing from type A, but one B and one C. That is the fourth way. So there are the 4 different ways. So I get coefficient of x raised to 2 as 4. Right? Similarly, one can verify for other values. So this is another nice way to use generative functions. Here is another example. Okay. So here you have an example of a sampling survey. So what is the sampling survey? So there are various professions of people. We have defined divided the professions to different categories, such as we have teachers, we have lawyers, we have doctors, we have engineers, right? So farmers, all these kind of professions are listed, and then from each of these n categories of people, right? We have for men as well as for M categories for the women, right? So out of these different professions, let's say that we fix n of them, right? Some n of them for men and some m of them for women, right? And then there are PI men available in each of the n categories. So category I, there is PI people, right? And QA ladies are available in each of the M categories. So, like category 1, I have Q1 people. Category M, I have QM people, right? So, ladies. And from this, we need to choose people for survey. Okay. So, we wish to conduct a survey by choosing totally K people, where we distinguish people of the same gender, right? Men and women are to be the same gender, if and only if they belong to different categories. I don't really want to distinguish in the same category. I don't want to distinguish between men and ladies. So how many different ways to do this? So if you have really understood the generative function topics that we have covered so far, you can immediately see the generative function for this. You can come up with very clearly, very easily, right? Because from the previous example, you get an idea about this also, right? So if I look at the function 1 plus x square plus etc. x raised to pi, that tells there is for the ith category I have precisely pi persons, and then I can choose some of this, like I can choose either one of them, none of them, two of them, or pi of them, right? So at most pi are there, so that is the choices from the first category. Similarly, second category I have 1 plus x etc. x raised to P2, right? So similarly, 1 plus etc. x raised to Pn. So for the n categories, I have the choices, and each one I write from the different categories. I can choose them to be in any way, and the product will tell you the number of ways of doing this. So that for product I equal to 1 to n, 1 plus x square plus etc. x raised to pi tells the choices for the men from the category, and then product j equal to 1 to m, 1 plus x etc. q x raised to qj, right? Gives the choices for the ladies from each of the m categories, and this is the product which is the generated function g of x. So the coefficient of x raised to k from this generated function will tell you the number of ways we want. And for what you can do is to take some numbers, fix the numbers m and n, and then PAs accordingly, and then take the product and find out the coefficient of x raised to k for some k, and then see whether it actually matches with your manual computation. So one can try this. Okay, so with that, we will change to a different topic now. In the next class onwards, we will look at a slightly different type of generative function. Okay? So at the moment, we will stop and continue in the next class.